The first speaker will be Bradley Nelson. He's a professor of robotics and intelligent systems at ETH Zurich and the chief scientific advisor of Science Robotics. He will talk about the robotics part of micro and nano robots. So, Brad, the floor is yours.
Okay, thank you very much, Carmen. I've been working in microrobotics since 1995, so it's almost 30 years now. But I actually started in robotics back in 1984. So when I got the invitation from Tamim to give a talk here at ICRA at 40, I started thinking back, 1984, that's when I started. I moved to Minnesota. I moved from Champaign to Minneapolis as a master's student, hoping to do control theory, and I wasn't able to find somebody doing hardcore control theory, but I found an advisor who was working in robotics, which is as close as I got, and Max Donath is that person, and I saw Max here. It's a pleasure to see him. So I started thinking about what was going on in 1984. I started reading research papers then, and these were some of the papers that caught my attention at first. First was on from Lou Paul, from the Penn folks, and on differential kinematics. I was interested, my master's thesis project entailed partly creating a robot simulator. I was using the Puma 560, so I used the equations from that paper. This is Systems Man, the cybernetics paper. It turned out there were some mistakes in those, and so being a lazy engineer, I started thinking, I heard about these thing called symbolic reasoning. And there was a paper that came out in that time by a guy by the name of Rod Brooks for his PhD thesis at Stanford on a program called Acronym. I also worked on an intelligent task automation project where they tried to use this to identify aircraft with geometric reasoning. So I used symbolic reasoning to derive all these equations. I had to learn Lisp, I had to learn Unix, I had to move from a PCAT to a Unix system and all that kind of thing. But there's a lot of papers that have really influenced me a lot. Rabert and Craig's hybrid position control came out in '81. Neville Hogan on impedance control in 1984. I kept thinking, how many seconds per cycle is it going to take for me to compute that on a PCAT? In 1985 at ICRA, Tsuneyo Yoshikawa published manipulability, and that was really a key part of what I was working on at the time and trying to understand how to do robotic assembly. And then a guy who's by the name of Osama Khatib also came up with something called a potential field approach, which used basically force fields or energy fields to try to guide robots. And so that still influences me to the day. And Dan Whitney had a very nice article that came out in '85 that kind of brought together all these areas of force control that was going on in the field. And then one of the coolest things I ever saw was this three-fingered robot hand from the early '80s from Ken Salisbury when he was at MIT. So these are the things that influenced me 40 years ago, and they still influence me today. When I started to build my own lab, my first lab in 1995 in Chicago, I basically took all the things I'd been working with, force control, visual servoing, active vision, and all these things, and started thinking, what if we did that under a microscope? High precision positioners, microscope optics were different than regular camera optics, and we started looking at some of the problems, like how to manipulate individual cells. And one of the first things we realized as we were working in this field was there was a gap in force sensing technology. There were the conventional force sensors we used at large scales, and then there was a gap at the small scales with atomic force microscopy, and we were looking at how to fill that gap because we realized when you're manipulating a biological cell, you really like to know how much force you're exerting on it. And so we spent 4 years trying to build a force sensor to do that, and that turned into a company called Femtotools. And so over the years, Femtotools we actually founded it when I got to Zurich in 2007, and it sells a number of products in microassembly, materials testing, and that kind of thing. It's been 17 years since we founded it. Finally exited the company. It was acquired a few months ago. But that, I think, was, when I worked in robotics and micro manipulation, I was really looking to get tenure and promoted. But the real impact of this, right, is little things you find, like there's a gap in technologies. How can we fill that gap, and what's the need there? And it takes often about 10 years to figure out what those needs are. But then in 2003, I started thinking, when I got to Zurich, just after a few months, started thinking it's not so interesting the processes as much as the devices we were making. At least that's what people seemed more interested in. And we started thinking about how can we create small devices that are going to move through the human body or move through the environment to clean water or these kinds of things. How can we make them move? How can we copy things from microorganisms? And bringing together the physics of that, the fabrication technologies, being bio-inspired has been quite rewarding over the last several years in this area. But one of the things that we've learned as we were going down this path is, how do you make these things move? We can't. It's difficult to put batteries on them, to put any kind of computation. And so we started focusing a lot right away on how to generate external magnetic fields to guide them. So we generate these fields and these field gradients to make them move in ways that we wanted them to move. And it took us a while, took us some years, but we realized that actually this problem of generating external magnetic fields with, in this case, a sequence of electromagnets, you see 3 up here, but we go up to 8, is really an identical problem to guiding to controlling a robot arm. For a robot arm, we put in joint velocities, we get end effector velocities. For our electromagnetic navigation system, or our electromagnet robots, we put in currents into each of these individual coils, and like I said, usually between 3 and 8, and we generate the fields and the field gradients that generates the torques and the forces on the devices that we're moving. And so that's a fundamental part of robotics, and when we realized that, it allowed us to go back to 50 years of robotics research and manipulator control and design and bring a lot of those lessons to bear on the microrobotics problem. So it's not only, though, moving microrobots, it's also moving things like small catheters with magnets on the tip, endoscopes, or guide wires. And so that's proven to be really one of the real interesting things. So thinking back to Osama's artificial potential field, he pointed out to me when he saw that, that's my stuff. That's the kind of stuff he was working on, right? Thinking about force fields, only that we're literally creating the force fields, not using them as computational elements to figure out paths. So, so what are we going to do with these things? And so one of the things we've been focusing on lately is treating ischemic stroke. Ischemic stroke is the second leading cause of death in the world. The leading cause is myocardial infarction, so these are vascular diseases. You want to get things into your blood vessels to remove these blood clots. It's also one of the leading causes of serious long-term disability. So there's a big social need to try to treat these kinds of diseases. And the current standard of care is something called a mechanical thrombectomy. So basically, a surgeon will put a wire into your femoral artery, guide it all the way up into your brain, and try to reach that blood clot, and then suck it out with a catheter, a working catheter they put over it. It is a classic non-collocation problem in robotics. You're often more than a meter away, you have a very flexible transmission, and you're trying to guide it from just pushing, pulling, and twisting down here, to someplace in the brain. So here's where we are. This is the kind of things we're working on. We do animal experiments. We have our electromagnetic navigation system. We have an advancer that pushes and pulls the guide wire, the catheter, and then this is in the animal clinic at the University Hospital in Zurich. And you'll see this is Dr. Gruber first manually places the catheter to get it near, and then uses, in this case, a PlayStation controller. We have a number of different input devices. And that tip is about 800 microns, less than a millimeter in scale. And he can drive it at will through the vasculature. So what are some of the advantages? Well, he's actually looking at it through X-ray images and guiding it. So he's actually controlling the tip of it. He's actually exerting the forces rather than being a meter away from it. But some of the other advantages are that we get much bigger ranges of motion. So on the left, the standard of care, you take a bent guide wire, you twist, you turn, you try to get into this region, and you have a very limited area you can reach. But with using magnetic fields to guide this, we have a much larger region that we can reach. We don't have to substitute different bends and catheters. We can use a single catheter to reach pretty much anywhere, and we can make these kinds of turns like this 120-degree, almost U-turn, that is simply not possible currently. And why is this important? Well, of course, we can get in, we can do this, but also when you have a stroke, time is brain, as they say, and minutes count. There's a lot of data out there that shows getting treated as rapidly as possible is important, and if you can get treated within 150 minutes of the onset of your symptoms, you have a 90% chance of walking out of the hospital functionally independent. So one of the problems, though, is there just aren't enough stroke centers in the world, and they're not dispersed equitably to reach these people. And we realize by going with co-located control, we actually now lend ourselves quite well to telesurgery. So we can actually control these devices from just about anywhere on the planet to any kind of a remote clinic that has the robotic system in place, these electromagnetic robotic systems. Recently, we did an experiment between Phoenix, Arizona, the Mayo Clinic there, back in Zurich, 9,300 kilometers away. We did a mechanical thrombectomy in a phantom. This is a human scale model of a human vasculature. And it was done completely from Phoenix with just my team back in Zurich, just setting everything up and getting it going. That green part represents the thrombus, the blood clot that's being taken out. And then more recently, we were we have a system in Hong Kong installed at the Multi-Scale Medical Robotics Center there at the Chinese University of Hong Kong. And my team in Zurich was then controlling it in Hong Kong. And it just so happens to be coincidental that the distance from Zurich to Hong Kong is almost the same as the distance from Phoenix to Zurich, by the way. But in this case, we're doing gastroscopy. So we have a little 4.25 millimeter diameter gastroscope that can go in your nose, into your stomach, and can do a complete gastroscopy, complete endoscopy to take biopsies, to look for cancer. 250 million endoscopies done a year. Millions of cases of stomach cancer discovered, and there just simply aren't enough of these done. So being able to do this remotely is a challenge, and but our system lends itself because of co-located control. But we're still thinking of microrobots. We're still working on getting these, and we're doing animals, and there's actually some companies that have raised quite a bit of funding to try to get there. So I really believe that in the next few years, we're going to see microrobots in humans treating things like glioblastomas in the brain, blood clots in the brain, or various kinds of diseases. So I want to thank you very much for your attention.
So are there any questions, please? Yeah, there is one there.
There is any kind of consequence to introduce that kind of wire inside the animals?
Well, yeah, that's why we do it in animals instead of people, because the consequences, you can rupture the blood vessel. So the surgeons who do this are extremely careful. They do it very, very delicately, and that's one of the advantages of our system, is that we can actually exert the forces and torques directly on the tip of the device to keep it in the center of the blood vessel. Also, we can make the devices much more flexible, so we leverage a lot of soft robotics, and that also gives us safety margins. And so we've actually shown this done some histology tests and shown that we can cause less damage to blood vessels than the standard of care.
But thinking on the apply on human, which is the next step to make it less dangerous?
So the way we make it less dangerous, we use very flexible tips, and we control the tip of it. And the way to make it less dangerous is to train your surgeons to use the devices properly. But we think there's, like I said, the histology tests we've done on placenta, we use human placentas to do tests on that, have shown that it's less damaging to the structure. So.
Thanks.
Someone else has a quick question.
So, thank you very much for this talk. My question is, do you develop also tools, for example, grippers, scissors, and sucking components? Maybe you use them in the kidneys or in the liver or elsewhere.
Yeah.
So that you can combine it with MRT or CT support.
Yeah. This is not compatible with MR, but it is with CT. And we develop grippers, for instance, for releasing devices. We're developing new types of catheters, endoscopes. We don't do cutting. That's one of the advantages when you're doing long distance control. We can tolerate delays up to half a second. If we were doing cutting, we'd have to have much higher bandwidth, these kinds of things. But yeah, these are active areas of research. There's a lot of tools being built in the lab. It's always difficult to get a device from the lab through FDA or CE mark into the clinic. That takes some very long-term thinking, I think.